Good afternoon, and our lecture today will look at map projection. Map projection. So we look at georeferencing, map projection, and they all revolve around the same area because map projection, what is it? It's a mathematical transformation, okay, from the round earth, the globe, to a flat surface. So the round earth to the globe, to a flat surface. Why do you want to do that? Why do you want to do that conversion? Because the earth is round. Okay. The earth is round. Okay, so the earth is round. There was a time where you couldn't even say that. The earth is round, or you could just say is the earth is flat or something like that. And then if you said it's round, then of course that brought trouble. You have to prove it. And then people have tried a whole lot to prove the roundness of the earth, if you like, the spherical shape of the earth, approximate spherical shape of the earth. And so, like I said, knowing the shape and size of something allows you to measure it. So straight away, map projections, georeferencing has to do with where, getting to know the location where you are. Okay, so coordinate systems, these are used, they all belong to the same domain, okay, of definitions and concepts. All right, so the concept of map projection is very important in GIS. Most of the data sets collected at a particular map projection. So, for example, you see a surveyor out there measuring, he eventually converts his distances and angles into coordinates. And these coordinates have to be in a particular, belong to a particular coordinate system. So there are different coordinate systems in the world. Not any two pair of numbers, are the same. Okay, in terms of the way they are derived and in terms of how they can be used. Okay. So it is very important to notice one, because coordinate systems also, relate to maps or representation of something, anything at all. Whether we are looking at a construction site, the grid on a construction site, okay, there's a coordinate system that applies. Or if we are looking at the whole Ghana and how the space is being utilized and used and managed, we still have to deal with numbers as in order to arrange things well and to know where things are. Are you okay? I mean, I don't want to go into double sale of land and all those things. Have their ramifications of not having, the right coordinate systems. Are you okay? And so we start off, let me just say, as novices, people are learning the principles of GIS by understanding the whole concept of map projection. Of course, and we can't talk about map projection without talking about what a map is. So we're going to have this conversation. We want to understand this. That's objective. The objective of every lecture is to make sure that the student have understood. They have understood what is being said. Okay, so if you're looking at my PowerPoint, then obviously you'll be seeing something on map projections or the map scale for now. I mean, I'm showing you map scale, am I? Yeah, I think I am. Okay, so the map scale, what is map scale? These are basic things you need to know. To know about any object, you need to know about its attributes and characteristics. So to know about a map, you need to know about some of the characteristics of the map. One of them is the scale of the map. Fundamentally, if I wouldn't make a map, if it wasn't for the fact that you could scale it, you couldn't make a map. Are you right? Or if like a plan, okay, it's a reduced version of reality. Okay, a map is a representation of reality. You understand that? So in reality, when you look around you, you know what reality is. If someone said, show me where Nigeria is, you'll be standing there and you go like, are you serious here? Because I have to get a map to show you where it is. because it's so far away from where you are. But Nigeria is so close to us than New York is. So we now begin to understand, yeah, the need for reduction. Are you okay? Reduction of distances. Are you okay? If some, we can also talk about reduction scale, meaning some areas of study. But obviously, the whole idea of MAP and MAP is the scale, because if it wasn't for that, you wouldn't be talking about it in the first place. And so what is map scale? Map scale is the method for expressing how map distance compares to ground distance, or the distance on the surface of the earth. Are you okay? So it's given by a simple equation of distance on map over distance on ground. So distance measured on a piece of paper compared to the equivalent distance on the ground will now give us what we call map scale. All right. So in the past, I've asked questions in exam where I was actually, teasing students with the idea of having something that appears on a map also on the ground. And I asked them, how do you determine the scale? Like, I mean, the kind of questions that we're asking these days are difficult. Are you going to say? You are supposed to think through it and understand the idea, the whole concept. Simple formula, but a lot of people now end up giving you answers. You ask yourself, where are they coming from? Okay. So mass scale is a very simple formula, but the question to you, if you are hearing me, is do you understand that simple formula? Distance on map over distance on ground. Very simple. It's not even one of the most complicated formulas I've ever seen, but it's difficult for people to understand it, which is really a shame. So you have the opportunity. I've told you everything that's happened in the past, the history of students that I've met and how they fared in terms of their understanding of what math skill is. So the question is that, do you understand? It reminds me of a song, really. I'm into music, so everything that I say also reminds me of a song. All right, but I won't sing it anyway. I'm tempted to. So let me share my whiteboard, and then I think you can see it now. Okay. So scale is equal to map distance. Okay. So distance on map over distance on ground. Simple formula. Every engineering student. This one is like JSS formula. Are you okay? JSS formula. But try to understand it. It's a temptation for you to think, oh, I've got it. And then you ask the question and you start thinking through it and you realize that it's not as simple as you thought. All right, so if I have 2 millimeters on a piece of paper, then I have 2 kilometers on the ground. What is the scale? Okay, you're supposed to know like basic things like this, so I will take my time and explain it. So you have to change the units so that they're all the same. They cancel out the units. So 2,000 meters, okay? Then 1,000 millimeters make a meter. 1,000 millimeters make a meter. So now you add 3 more zeros, then you get millimeters. So I've just converted 2 kilometers to meters to millimeters by adding zeros. Okay. And remember that it doesn't always have to be like this. You can have inches and miles. So think through as an engineer, you can travel to the US to go and work. Get ready for that. Okay, so here I can just cancel out the millimeters. Okay. So let me use red so that it looks more interesting. And then I have 2 over 2 million. Okay. Okay, so there's what we call the representative fraction scale. So normally you find the scale of a map and then you have 1:something. So you see 1:2,500, 1:50 in some engineering drawings. Okay, so I've divided both sides by 2. Okay, of course I could put 2 here and put 2 here, right? And I go further down, and then I'll have 1/1 million. Okay, so the scale of a map, okay, in which an object on the ground is, about 2 kilometers in length, okay. If the object on the map is 2 millimeters, then the scale of the map is 1 in 1 million. Okay, so I assume that I'm teaching level 400s. They probably know this and they know it too much that I asked a question in exam, and then what I did, that was like a big trap, yeah, barbed wire or something that cut them up. Are you okay? So take note of it, that as we teach, we have expectations, okay, and this is university, so we try to also make things look more interesting in terms of knowledge. So if you don't get it, please sit down with your friend, go over it, try to understand how this was done. 1:1 million is the map. So I can write a story. Of course, when we ask you questions, we put it in the form of a story, like a case study, okay, that this is happening, you've been asked to go here, there's a river that is, you should be able to figure out which one is the ground distance and which one is what the, map distance. It's very important. Any questions, you can ask me, you can put up your hand anytime, but I'll move on anyway, yeah? Okay, so that's it. So what you see on the left hand side is the graphic scale or the scale bar. So which means that we can actually draw it up. Okay, we can take a ruler and simply measure in millimeters. And then we know that every 1 millimeter, every 2 millimeters, we have like 2 kilometers. Or every 1 millimeter, we have 1 kilometer. And then begin to shade it. Then we get what we call a scale bar. Okay, it's a graphic representation of scale. Then we can also talk about, so we have the representative fraction scale, we can have the scale bar, the graphic scale. We can also have a verbal scale. So I can just use my mouth to say 2 millimeters represent 2 kilometers. So these are things that I think we should know. Okay, there are things if you don't know, it's not good, even if you're not an engineer. So even if you're an engineer, then the expectations are high. All right. So large scale, small scale maps, what is the difference? You should also know that large scale, we can distinguish between objects. When you take a large scale plan or map, normally large scale maps are also called plans, okay? And when you get to smaller scales, then of course. Now when we say large scale, then the ratio becomes large. So 1 divided by 2,500 is greater than 1 divided by 1 million. So in that case, 1 divided by 2,500, 1:2,500 scale is a large scale compared to 1:2 million. Okay. All right. So a smaller scale number means a large scale. A larger scale number means a small scale. Take note of that. Okay. So these are some basic qualities of a map, but there's more to a map than that. That of course maps are made up of symbols and all that. Okay. My focus this afternoon is on the concept of map projection. So, but I wanted to just touch on one quality of a scale of a map, which is the scale. All right. But obviously, maps are simply made up of symbols, scales, okay, north arrows, and things like that to guide you, to help you orient. Great. So map projection concept, all right, is as a result, the need for it is as a result that we may need to actually do a coordinate transformation. Why? Because we have different coordinate systems that exist. Okay. Well, what you know to be coordinate systems are what they are. You have y-axis, x-axis, that is coordinate system, and x-y, combination of those pairs of numbers give you a set of coordinates. Are you okay? Which belong to the domain of values within that axis. Are you okay? What that the axis define, whatever the axis define. Okay, all right. So integration of data into our GIS makes it fundamental that we understand the concept of map projection, because we receive data and then the data may not be in the projection of interest. Therefore, get to know what the projections are. Once you get to know what they are, then you know exactly how to transform them, all right? But then you can't be transforming, I don't know, fried rice to jollof when you don't even know how to cook rice. you don't even know the concept of cooking rice, that you just don't put in a whole lot of water, you end up with rice water. Are you okay? So we want to understand the very fundamental of what map projection is about. Then we can look at transforming one projection system to another. All right, so you can see that on this diagram, we see the whole earth, the F in there, okay? Then we have the map on the right hand side. So the earth, the round earth to a flat surface. So that's the whole thing, this round object to flat surface. And that is a mathematical transformation. It's okay. Whether you treat the earth as a sphere or as a spheroid, you must transform its three-dimensional surface to create a flat map sheet. Period. Are you okay? So sphere versus spheroid. So a sphere is perfectly like a circle that has been revolved, okay, around an axis. But a spheroid, it's not really symmetrical all around. In other words, you can't define a spheroid with one radii, but you will need to define a sphere with just one. Are you with me? So the spheroid is more like a flattened kind of sphere. Are you okay? All right. So that's how the Earth really is, approximately like that. What it means is that at the poles, at the North Pole and the South Pole of the Earth, there is a flattening that happens there. Are you okay? So there's a need for us to understand, are you okay, these concepts. It's convenient, it's a convenient surface to deal with when you look at the globe. Are you okay? The globe is a convenient surface to deal with. The globe is a convenient surface. Okay, hold on, guys. I have to talk to you. Yes, so let's carry on. It's convenient surface. The globe is a convenient surface. The earth is round. So, yes, we keep it like that. Okay, the earth is round. And so you don't have to use something else to represent it. So the ideal way of representing the earth without distortion or error is to use the globe. Are you okay? So that's what I mean by it is convenient surface to deal with as opposed to three-dimensional surfaces. It's okay. I mean, I'm referring to the flat surface in this case. The flat surface is convenient. Okay? So what does it mean? It means we don't go around with the globe. If you have a project, you don't say, well, I want to have very high accuracy work done. So I have the whole earth in my armpit. I've represented the earth as it's supposed to be, and I'm holding a globe under my armpit. You don't do that. Okay. What you do is that you use a flat surface. You use a sheet. Every engineer holds a flat sheet, and on which he has his drawings and everything. But you can see that it's a fallacy. Why? Because you are working on a round surface. Okay, we know you want to project everything, get your work done. There's a reference, there's a baseline, a base datum based on which you are actually constructing in order. But then you need to recognize that the surface you're working on is not flat. Okay? So map projection is a mathematical concept. Okay? This mathematical transformation is what we are calling map projection. This whole idea of transforming a round surface to a flat surface is what we are calling map projection. So let me just switch back to my whiteboard, and then let's look at a few things. So you have the round earth. Okay, so the best way that we've tried to represent the round earth is drawing a round surface, having a north pole, having a south pole, and then drawing some lines. These are actually circles, great circles, like that move from the north pole all the way to the south pole. They are called the longitudes. Okay, all the lines that go through the north pole and the south pole, they go all the way around it and back. They are called longitudes. Okay, so longitudes. And then we have the lines that move, along the surface of the earth. We want to call that the latitude. So one of the popular latitudes that we all know of will be the equator. So that is the equator. We will find out why it's the equator. It's a reference latitude. Is that okay? All right. So latitude. latitudes and longitudes, if you heard about that, you can use that alone to fix your position. So most of the time when you use a GPS receiver, what you have in your hand or the values that you get, the data that you get from a GPS receiver, they are longitudes and then latitudes. So the symbols are put on there. These represent the longitude and latitude. This one is called lambda, and that is called phi. Is that okay? So lambda and then phi. Okay, these are the longitudes and latitudes. Okay, so North Pole is up here. The Earth bulges at the north, the poles. Yeah. Okay, and then we have the latitude. The latitudes are also called parallels. Okay, so let me write that down for you. The latitudes are also known as parallels or parallels if you don't want problems. Are you okay? If you're R and you're L, then you just say parallels and you're free. Then you have the longitudes. They are also known as meridians. Are you okay? Meridians. So that's why we have the Greenwich meridian. If you've heard of the Greenwich meridian, okay, that's another name for a longitude. But the Greenwich meridian is a reference longitude, just as the equator is a reference latitude. Okay, so the equator is a reference latitude, 0 degrees. Okay, they are all measured in degrees. I'll explain to you why that is the case. Okay, so the Greenwich meridian is a longitude that actually goes through a town in the UK called Greenwich. Okay, so 0 degrees. What it means is that every other longitude is measured with reference to this line. So in this case, that is the Greenwich meridian. GM, it goes through Tema. Are you okay? So people are, there's even a song that mentions meridian in it. I don't know. I keep on asking people. The song is actually in Ghana, and I don't understand that. So I don't know why they were mentioning the name meridian. Are you okay? I can't sing it. I'm shy. Are you okay? So let's move on. So when you look at this pic, you should be able to appreciate the whole idea of the globe and the representation of the globe. So you go to a lot of offices, you see globes sitting there, but I don't think they have an idea. I hope so. I don't think so. Not everyone, but most people may not have an idea why the globe. Why the globe is the best way to represent the earth. It's the ideal way without any distortion. All right. So take note of that distortion. In our bit to represent the earth, we do the projection. Are you okay? In other words, we want to actually find a convenient way to represent the round earth, and we make use of a projection and then have it on a flat surface. Okay, so let's now do this round surface to flat surface. So all the longitudes and latitudes will now turn into straight lines. Are you okay? And then they will distend as we approach the North Pole. So the North Pole will be here somewhere. Are you okay? And then as you go here, then we have a distension. It's like a stretch. Are you okay? And that stretch is a distortion. So as we approach the North Pole, then our projection tends to have a lot of errors in it. Now there is a political, undertone to it, and people say that the U.S. is not as big as it is. Canada, they may not be as big as they are because of this distortion, this distension. Okay, so what are we doing with projection? Let me just put this down that as we try to project from longitude and latitude to, a more of a Cartesian coordinate system, we are having lambda and phi being converted to x, y. Okay, so mathematically, this is what we are doing. Okay, so we can write x, y as a function of lambda and phi. Okay, so we can actually write x as a function of lambda and then phi. Okay, so this is in other words saying that we can write a formula that converts longitude and latitude to x, and then we can do same for y. Okay, so that is what the map projection is about. At the end of this application of this formula, we are going to be able to now plot as if we are plotting XY coordinates, which any GHS person can do. Okay. All right. So this formula is actually stated is in your handout. I'll just give it to you. What I'll give to you, and then you can just use that. Okay. So there are different ways of actually converting from longitude to latitude. People have come up with all sort of ideas. One of them was to make use of a developable surface, such as a cylinder. So we have the Earth as a round surface, and then we have a cylinder. We fit it with a cylinder. This is a mathematical process. This is not like we are fitting a cylinder to the Earth. You can't do that. Okay. But then if we actually reduce the Earth to some kind of spheroid, okay, or a sphere, then we could now do this. So you fit a cylinder to the Earth, and then you actually project as if you have a light source in the center of the globe, and then we are actually pushing all your longitudes and latitudes onto a flat surface. So then you have something like that. So this is your flat surface, okay? And then all your longitudes appear as such. Is that okay? All right, so we can also decide that, okay, we're going to use a cone for that purpose, for the transformation purpose. So we have the Earth, then we have a cone that fits at the top, okay? And then we can now split the cone, and then we have something looking like this, okay? Okay, so it's like we have these surfaces that we are putting onto the Earth, and then we are projecting onto it. This is the best way to actually convert. I don't know if there's any other convenient way of doing it, but this has in the literature is the best way. You can also decide that, okay, I'm going to put a flat surface to it and then still transform it. Then you still have a projected surface. Okay, so the unprojected coordinates are normally longitudes and latitudes. Okay, they are also known as spherical coordinates or geographical coordinates. And then the projected coordinates will be X, Y. These are projected coordinates. And then the coordinate system can be named. So we are going to learn a few names that can be given to these three transformations. Okay, so when we use a cylinder, we want to call that cylindrical projection. Simple as that. Cylindrical projection. When we use a cone, we want to call that conical projection. And then when we use this flat surface, we want to call that azimuthal, azimuth, yeah? That's the base word, azimuthal projection. Because it's normally used at the poles. Okay, so I guess that would be the reason that it's being called that. So these are the classes of projection. We can have cylindrical projections, conical projections, azimuthal projections. Cylindrical projections are very good for tropical areas, okay, like parts of Africa, okay, in the tropics, is okay. Parts around the equatorial regions, we can use the cylindrical projection. And then we can also make use of the cone around, the temperate regions like Japan, parts of Europe can make use of conical projection because they preserve the shape, okay? Or let me just say the area. So every map has some sort of distortion, and I'm not going to go into the deeper ends of it. We can look at equivalent maps, equal area maps and all that. So for a pilot using a map, they may choose to go for one of them. Now, okay, I'm not interested in the area. I'm interested in just direction. I want to make sure my direction is accurate and all that. So depending on the purpose of the map, a certain type or class of projection is used. So for conical projection, like I said, the temperate regions, it works very well with them. For polar regions, we want to go for the azimuthal. Another name for the azimuthal is stereographic projections. So graphic. In fact, there are so many names under azimuthal and stereographic projection. You can have the mnemonic, okay, you can have the orthographic. I just want you to be aware that there are so many options that we have when it comes to how the earth is represented. Why? Because the earth isn't flat. That's why we are struggling. Okay, that's why people will come out with all sort of, in fact, different countries have come out with their own coordinate systems. Can you imagine that we had the War Office? Of course, War Office, what does it remind you of? Probably remind you of World War and all that. Okay. Of course, after the World War I, World War II, and all that, in the 1940s, people started thinking, let me just say, there was a wake-up call. Are you okay? And a lot of inventions and people came out with new things. Okay. And so some of these things are almost surprised. That's what they came from. But people have over years tried to understand the shape and form of the earth. So we don't only have these classes of projection. Let's look at what we call the aspects of a projection. So you can decide that, okay, even though I want to use, excuse me, a cylindrical projection, I want to have it in a transversal orientation of the cylinder. So you can imagine, let me actually use red to depict the cylinder. So if I have the cylinder going this way, then in that case, the axis of the developable surface is perpendicular or orthogonal to the axis of rotation of the earth. So if the earth is rotating this way, which it is, are you okay? Otherwise, you wouldn't have your day and night. Then you have the axis of the cylinder being perpendicular to it. This is what we call the transverse aspects. The transverse aspects. So transverse aspects. Okay. So the first one, all the orientations you have at the top are the normal aspects. So you can have three aspects. So let me just list them. You can have the normal aspects. You can have, we have 10 minutes after that. Let's use the same link to rejoin, please. We can have the transverse aspect. You can have the oblique aspect. Okay, so we can have three aspects. So what is the oblique aspect? Quickly, we know what a transverse aspect is. It's in between the normal aspects and the transverse aspects. So you can imagine that if you have the earth like that, then the oblique cylindrical projection will look more like this. So the cylinder is tilted. Meanwhile, the North Pole remains where it's supposed to be, up here. South Pole remains the same as this one. South Pole is down here, North Pole is on top. So North Pole, South Pole, but then there's the cylinders changing. Are you okay? But this is mathematical. Don't be imagining someone holding a huge cylinder. Okay, Captain Planet could do that. I don't know if you watched Captain Planet before in the 80s. If you're old enough to have watched Captain Planet, you know what I'm talking about. He could do that, but it's not possible. Then what I'm talking about is only mathematical. It's assumed that we are dealing with the globe, a small representation of the earth. Of course, because like I said, because of reduction of scale, the use of scale, we can always describe things like this. The earth has now been reduced into a small circle on my laptop. Are you okay? All right, so we have three aspects of the map projection. So we can have three classes: cylindrical, conical, and then we have the planar, azimuthal. Yeah, planar is the same as azimuthal, same as stereographic. Then we can have three aspects. Are you okay? All right, so you cannot try it now if you are even listening to me, which I suspect you are not. Take a pen, take a paper, and then do one for me right now. You can do the transverse, conical projection. Do it for yourself. If you understand it, you can do this in 2 seconds and we all can move on. Transverse conical projection. how would it look like? Okay, you can just do that yourself to test if you understood what we talked about. Okay, so it's going to look more like that. I'm sure by now you've drawn it. Okay, so where the developable surface touches the air, the distortion is less. That's the whole idea with map projections. The developable surface, the farther away you are from it, where it touches it, the earth, the more distortion you have. Also, the wider, the less compact a country is, the more the distortion, the higher the distortion. Are you okay? So you're going to have more distortion for any country. So that's why you want to actually localize the whole projection. If you want to develop a coordinate system, it has to be for a smaller area. Okay. All right. There's something known as, or that we all need to know with the conical projection. Let me talk a little bit more about it. Okay, Benjamin's hand is up, so I think I like that interaction. So let's hear you, Benjamin.
When you say compact,
Yes.
I don't understand.
Okay, where the surface touches the earth. So you can imagine trying to take some round thing, a round object, and then take a flat object. So I wish I had some ball here. I don't, but you can take anything, I mean, in your house that looks like a ball, and then take a flat surface like a book, and then try to touch it with it. Are you okay? You realize that it doesn't kind of flash with it. That's the word I think I should use. It doesn't flash, it doesn't become, it doesn't touch it, you know, at all points. Okay, so you are going to have a distortion as you move away. Let me just show you on the board. So if I have this and I put a flat surface and I try to project, so the whole idea of the projection is that you are actually projecting light rays, okay, are projecting the longitudes and latitudes onto the flat surface. That is the whole idea. That's another way to look at it. Okay. So because you've asked a question, then I have to go further and draw this diagram. But you will not be asked to draw this diagram. I don't expect you to know this detail. I only need you to understand the concept. So let's assume we have a light source in the middle of the earth, and then the longitudes are on the surface of the earth. Is that not so? So anywhere you are on the surface of the earth, you can know your location via a longitude, which is a line from the top of the earth, North Pole to the South Pole, okay? And then, so there's intersection of that longitude and the latitude gives you a location. Is that not so? Now, you realize that we can't work with the longitude and latitude because we want to actually work on the flat surface. Okay, so we are now making use of a projection. Now, so the projection of the longitudes on the surface of the earth, okay, let me use blue to do this, onto the flat surface, okay, that projection is called, there's a mathematical, I don't want to go into the mathematics. You have to now consider the radius of the earth. Please, let's not go any further. Okay, the radius of the earth has to be considered. And then the distance that was actually on the surface of the earth. Now watch this one, Ben. This distance here now is now getting larger. Okay, so we were here. This was the distance from here to here. And then now as we projected it, we have a new distance, which is not the same as what it was on the round surface. Why are we having this problem? Because we simply wanted to have something that is round on the flat surface. Now this creates a distortion. So the touching that you're asking about happens at this point. Okay, this is where the flat surface, the developable surface, the flat surface, or the cone or the cylinder touches the earth at a certain point of interest. So the area to be mapped is where you want the surface to touch. Are you okay? Maybe it's not going to be easy for you to understand it, but try very hard, you will get it. In concept, we have a surface that touches the area that is to be mapped. Are you okay? And then we are projecting the things that are on the surface of the earth, which is round, onto something that is flat. Okay? And so
Okay,
there is a distortion, there is an enlargement that now, instead of having this distance here, we are now having a longer distance over here. Okay, now we don't have that case where the developable surface touches the earth in this, at this point, this, for example, here, because it's touching it. So the farther away you are from the point of tangency, the larger the distortion. Okay, can you kind of follow a bit? Ben, are you cool?
Yes, it's like using a torchlight and at the source.
That one is making it clearer, isn't it? Exactly.
Yes.
Exactly. So when you take a torchlight, you realize that the farther away you are from the torchlight, the person is holding it, then you see that your figure begins to get distorted. Are you okay? So your shadow gets distorted if you are farther away from the torchlight, if you are not facing the torchlight. So now you are far away from the point of tangency. Like, we can do that analogy. Is that okay?
I get it now.
Yes, it's not, because there's more detail to it. So yeah, but I'm happy you are getting it. Okay, we have 1 minute, so we are ending this session here, and please let's join with the same link. My projection works like that. We can take the cone and look at that too. Is that okay? You can take the cone, put the cone on it, and then project the longitudes onto the cone. Then again, the cone will be touching the earth at a certain point. Okay, so, but the interesting thing with the cone, I will teach when we come back. I'll show you, I'll explain something to you about the cone, that the cone has what we call the standard parallel. The standard parallel, and it can actually cut the earth. We can choose to cut the earth at 2 points where we have two standard parallels. The whole